Real exam questions. This is question 52 about slab design with yield lines. What is the maximum mobile load in characteristic value in ULS persistence of a slab with fixed end supports on the two sides, where the bottom reinforcement is equal to diameter 12, center to center 200, and a top reinforcement of diameter 10, center to center 200. Use the yield line theory. Concrete cover is 40 millimeter, depth of the slab is 240 millimeter, and concrete quality is 30 megapascal. The two other sides of the slab are free. Which of the mentioned data do you not need to determine the load-bearing capacity and why? This is our slab. We know that the reinforcement at the bottom, the positive bending moments, is equal to 5 diameters 12 per meter. That's diameter 12, 5 per meter, gives you 565 square millimeter per meter. The top reinforcement or the negative bending moment, there you have a reinforcement of diameter 10, center to center 200. It gives you 393 square millimeters per meter. The plastic bending moment, by definition, is equal to 0.9 times the lever arm times the yield strength of the steel times the reinforcement. But because we are using an upper bound method, we have to use 10% more reinforcement or 10% less bending moment. The bending moment at the fixed end supports or the negative bending moments, m, is also by definition equals to this, but with the top reinforcement instead of the bottom reinforcement. So this is the bottom yield line of the bottom reinforcement, and these are the two yield lines of the fixed end supports, and it's m times the value of the positive bending moment. So out of those two, we can calculate mu, and because mu is proportional to the ratio of reinforcement, and mu is here 0.7. Mu is 0.7, so the work done by the internal forces is this yield line projected to this axis of rotation and to this axis of rotation. So we have 2 times m, because this is m, 2 times m, multiplied by the angle of rotation, which is of course delta divided by 2.15, half of this distance. We also have two yield lines at the fixed end support, so 2 times. The bending moment is mu m, so it's 0.7 times m, and the angle of rotation is delta over 2.15. So d is equal to 1.58 times the plastic bending moment of the positive bending moment. The work done by the external forces is, of course, the total load, because we have two rectangulars together. So it's the total load, which is 4.3 times 1 meter width, gives you QD times 4.3, and the mean deflection of a rectangle is delta over 2, gives you a total of 2.15 QD. Now we know that those should be equal. E is equal to D. And from that, you can calculate M. M is the bottom bending moment, or the positive bending moment is 1.36 times QD out of this equation. And on the top, MT on the top is mu M, and M was this. So that's multiplied by 0.7 gives you 0.95 QD on the top. So now let's have a look at the top reinforcement. The reinforcement was 393 square millimeters per meter. The lever arm is the total depth of the slab minus concrete covers minus point of gravity of the reinforcement. So this reinforcement is in the third layer and it gives you 195 millimeters. The plastic bending moment that you can take up with this reinforcement is then equal to, of course, it's equal to 0.9 times the lever arm times the yield strength of the reinforcement and multiplied by the reinforcement and divided by 1.1. And it gives you 27.27 kilonewton meter per meter. But we also know from the previous slides that the top bending moment is equal to 0.95 times the load. So the load based on the top reinforcement is 28.71 kilonewton per square meter. But now check the bottom reinforcement. The bottom reinforcement is 565 square millimeter per meter. The effective depth is the total depth minus concrete cover minus point of gravity. It's 194 millimeter. The bending moment, the plastic bending moment that you can take up with this reinforcement is then 39.01 kilonewton meter per meter. But we've seen from the previous slide that the bottom bending moment is equal to 1.36 times QD. So out of those two, we get QD equals 28.68. You see, it's almost the same. We take, just out of principle, the lowest value. The load is then 28.68 kilonewton per square meter in ULS persistence, but the load is defined as 1.35 times the dead load or proper weight times 1.5 times the mobile load. And out of those two, we get that the mobile load is equal to 13.7 kilonewton per square meter. FCK, the concrete quality, is not needed to calculate the bearing capacity. We did not use in the formulas FCK. This is because the method of yield lines implies that the reinforcement will yield before the concrete crushes. So the total bearing capacity of the slab depends on the concrete strength and on the steel strength. So the first one who is going to give in, this gives you the maximum load. So, and the method of yield line, by definition, counts on the fact that the reinforcement will first yield. And the second element that we are not using, that is the width of the slab, 6.3 meter. This we don't use because the bending moments we have calculated per meter width. You can include the width, but you do not need it. It drops from both sides of the equation.